Hello everyone and welcome back. Today I will continue talking about the last part of reactions in aqueous solution, the oxidation reduction reactions. I covered before the precipitation reactions, the acid-base reactions. Today I will cover the oxidation reduction reactions. Oxidation reduction reactions actually classified into combustion reactions, displacement, disproportion, and combination reactions. Displacement can be either hydrogen, metal, or halogen displacement. Oxidation reduction reactions involve electron transfer. You have electron transfer between the species, which will change the oxidation number of each species. Also, oxidation reduction reactions occur in water. Some of those reactions actually occur in absence of water. Oxidation reaction is a half reaction that involves the loss of electrons, and the reduction reaction is the other half, which will involve the gain of electrons. Let's look at one example, the reaction of magnesium with oxygen to form magnesium oxide. If I try to balance this chemical equation, I will have two magnesium atoms on that side and two magnesium oxide on that side. So now let's write the ionic equation. For magnesium, the two magnesium, it will involve the loss of electrons, so it will form magnesium ion, and you have 4 electrons is lost for the two atoms. As for the two ions, as for the part that involve oxygen, oxygen actually will gain the 4 electrons, forming oxygen ion. I have 2 oxygen ion in that case, and if I try to write the complete ionic equation, this means that I write this part of the reaction and that part of the reaction, and the other half, which is a product half, plus, and the last part, which is the 4 electrons. You could see that if I cancel this, the two parts that appears on the both sides of the reaction, I will cancel the electrons. So this is why oxidation reduction reactions actually, although it involves the transfer of electrons, the sum of those electrons, if I try to look at net equation, it will be equal to 0. In that case, if I looked at magnesium, it started with oxidation number which is equal to 0, and it transferred to 2 positive. So magnesium became oxidation number became 2 positive, while oxygen started with 0 and it ended with -2, which is the oxidation number of oxygen in case of magnesium oxide. Now let's look at some oxy-reduction reaction associated with color change. Now if I looked at some oxidation reduction reactions associated with color change, one example is this, the reaction of zinc with copper sulfate to form zinc sulfate, and copper will precipitate. I start by the blue color of copper sulfate that is lost in case of the formation of copper. So the color change here from blue, and it will disappear. The second example is the formation of silver mirror, or the precipitation of silver mirror in the reaction, which copper would react with silver nitrate to form copper nitrate plus silver, which will precipitate. In that case, if I try to look at the net ionic equation, it will involve copper, and I have silver here with only 1 positive. I have 2 silver atoms, and in that case copper is transferred into copper ion, and silver will be silver metal. Now, if I looked at the oxidation reduction reaction of zinc with a strong acid, in that case, if I add some pellets of zinc in hydrochloric acid, the ionic equations that involve the formation of zinc ions and the formation of hydrogen which will evolve. This equation can be split into two equations. One of them will be the oxidation reaction and the other one is the reduction reaction. The zinc atom will be oxidized, so as we see here, the zinc metal is forming zinc ion. This means it will lose electrons, and this loss will be 2 electrons, and the other half, which is the reduction reaction, involves the gaining of 2 electrons for the acid. So hydrochloric acid will gain those 2 electrons, forming hydrogen gas, and this will involve the other part or other half. So this is the reduction half and this is the oxidation half reaction. Now you have to keep in mind, in oxidation reduction reactions, it have to happen together. So you can't have only oxidation reaction or only reduction reaction. Both of them have to occur at the same time. There is no net charge in the number of electrons. This is why when we cancel the electrons on both sides, when we try to cancel the number of electrons on both sides, we saw that we cancelled the all electrons, because actually that transfer happens between both sides. The oxidation will lose those electrons, which will be gained by the other half, so that there is no net charge. And those give off in the oxidation reaction are taken usually by the other species, which we will name them the reduction half. Now the oxidation number. The oxidation number is the actual number of charge on each atom. You should calculate when oxidation reduction happens. You should calculate the oxidation number. Oxidation number of or oxidation state is a number that signifies the number of charge or number of electrons that have been gained or have lost. In here you could see it is a partial transfer of electrons. Still oxidation number should be calculated in that case. So if I try to calculate the number of electrons in that case, I could see that it started with 0. Any molecules, the oxidation number is equal to 0, while in that part it should be, because I have a net my net charge should be equal to 0, like we've seen in that slide. So I should have no net charge, which means this should be equal to 0 as well. If I try to equal this part to 0, knowing that I know that my hydrogen is equal to +1, this means the chlorine atom oxidation number is actually -1. Now the rules that I should follow when I assign oxidation numbers, I should remember that free elements have 0 oxidation number. Example for that, hydrogen gas, barium, sodium. So any element, free element, the oxidation number should be equal to 0. The oxidation number of ions is the charge on the ions, which means for lithium I have 1 charge, for iron I have 3 positive charge, and for chlorine it is just 1 negative charge. A nitrate is 1 negative charge. The oxidation number in oxygen generally in most cases is -2, but in peroxide I will assume that I will calculate it to be -1, and superoxide it is -half. Oxidation number of hydrogen is equal to +1, except for when it is bonded to a metal. In that case, it is the only case where hydrogen will be equal to, oxidation number will be equal to -1. Halogens have -1 oxidation number in general, except when it is bonded to oxygen. In that case, in oxo acids have a positive oxidation number, and I have to calculate it each time. Neutral molecules oxidation number is equal to 0. So if I have something like ammonia, I have the total number will be should be equal to +1, while for NH4 Cl it's equal to 0. So in that case, if I'm calculating for the neutral molecule, it it will be equal to 0, but each part of those ions will be assigned to the number of ions on the top, or assigned by calculating the oxidation number of each part of those ions. In here I have the nitrogen, which is equal to -3, and for hydrogen we agreed that it should be equal to +1 unless it is an alkali element. In that case, it is +1 multiplied by 4, so the total is actually +1. But both parts, the NH4 and Cl, both of them should be equal to 0. This is why I will assign the oxidation number of chlorine to be -1, so I can have this total number which is equal to 0. The oxidation number can be fraction, like oxygen in superoxide, which is -half. So I can have a fraction, not just whole numbers. Now let's look at some examples. Our first example assigns the oxidation number of chlorine atoms in each of the following compounds. The first compound, HClO4. For HClO4, the whole molecules should be equal to 0, and we agreed that I should write down for hydrogen, which is equal to +1, and we assign the oxidation number for oxygen to be +2, so -2. So in that case, if I assigned for the hydrogen to be +1, and I still don't know the oxidation number of chlorine, in that case, plus I have 4 atoms. Each one of them is -2, and the total should be equal to 0. So if I multiply the 4 by -2, which is equal -8 plus 1, this means -7. Then I flip it to the other side because I need to find out the oxidation number of chlorine. So I move the -7 to the other side. In that case, chlorine in that case is equal to +7. Let's look at the second example, chlorine O3, ClO3 minus. In that case, my total net charge is actually equal to -1. So unless it is indicated here, it is equal to 0. But you could see that here I already written a minus, so the total for this equation should be equal to -1. We agreed that oxygen is actually equal to -2. So if I try to assign the oxidation number, in that case it is 3 multiplied by -2, and the total should be equal to -1. So the 3 by 2 is equal to -6. I move it to the other side. This means the chlorine atom would be equal to +5. Now let's look at the first type of oxidation reduction reactions, the combination reaction. It is in combination reaction, one or more substances will combine to form one single product. If I looked at one example, is the combination of sulfur with oxygen to form SO2 or sulfur dioxide. If I try to assign the oxidation number for this is equal to 0, and for that part is equal to 0, and the sum of SO2 is equal to 0. So the oxidation number for oxygen, like we agreed before, it's -2, and I have 2. So if I try to assign the for the sulfur, in that case sulfur is equal to +4. If I looked at another example, the combination of aluminium with barium to form AlBr3. In that case, this should be, if I try to balance my chemical equation, this is the balanced chemical equation, and the total oxidation number for aluminium is metal is equal to 0, and the barium gas is barium liquid in that case is equal to 0. And for this part, for aluminium it is +3, and for barium, like we agreed that halogens, all halogens is -1. Not all combination reactions are oxidation reduction reaction. Example for that is the combination of calcium oxide with sulfur dioxide to form calcium sulfite. In that case, this calcium sulfite If I try to look at the oxidation number of calcium, the whole compound here is equal to 0. So for calcium it's equal to positive 2, and for oxygen is equal minus 2, and here in sulfide, the sulfide we calculated before to be equal to positive 4, and here is minus 2. For calcium, in that case, if I try to calculate it, if I know now that this should be equal to positive 4, and for oxygen it's minus 3, each one of them is minus 2. So I have 3 if each one of them is equal to minus 2. So and the total in that case should be equal to 0. So for calcium, if I assign the oxidation number for calcium in that case, it should be equal to minus 6, so it should be equal to positive 2. If I looked at the total oxidation number on both sides, here is positive 2 and here is positive 2, here is negative 2 and here is negative 2, and for sulfur both sides is positive 4. This means there is no electron transfer. All my atoms didn't lose or gain any electrons. The oxidation number remained the same on both sides. This is why I cannot consider this reaction to be oxidation reduction reaction. So be careful with that. Not all combination reactions are oxidation reduction reactions. You have to assign the oxidation number for each part to know if it is oxidation reduction reaction or not. If I looked at the oxidation number of elements in the periodic table, the oxidation number of all group 1A, it is positive 1 except for hydrogen. It is always positive 1 except with metals, it will be negative 1. For group 2A, it will be equal positive 2. The general oxidation number for group from 7A to 4A will be equal to 8 minus the group number, and the answer should be and my oxidation number should be in negative. So if I looked at something like fluorine, in that case it is in group 7A, so 8 minus 7 is equal 1, and I always write the negative, so it is the general oxidation number, the common oxidation number would be equal to minus 1. If I looked at oxygen, if I try to calculate it for oxygen, so it is 8 minus 6. This means it will be equal to, I always write the negative first, and it is minus 2, and so on. If I looked at the transition elements, their oxidation numbers varies, and most of them carries the oxidation number of oxidations similar to their group number. Now, if we look at another type of oxidation reduction reaction, the combustion reaction. It is a reaction in which a substance reacts with oxygen. Usually, there will be a release of heat and light to produce a flame. Example for that will be the oxidation of C3H8 propane in presence of oxygen to form carbon dioxide plus 4 water molecule. If I looked here at the oxidation number of oxygen, generally in a combustion reaction will be from 0 to minus 2. Now moving to displacement reactions. In here, ion or atom will be displaced by another ion or atom. First, let's look at the displacement of hydrogen. Hydrogen can be displaced from water by alkali metals and some alkaline earth metal. Example to that, if I have sodium plus hydrogen of water, it can be displaced. This is hydrogen in water will be displaced, and the sodium hydroxide will form, and hydrogen will evolve. Now, if I looked at the oxidation number in that case, for hydrogen it is the positive 1, and for sodium in that case it is 0, and on that side both of them is actually positive 1, and the oxygen is negative 2. Another example, the displacement of hydrogen with calcium. So calcium will displace hydrogen in water to form calcium hydroxide plus hydrogen gas. Hydrogen also can be displaced from their acids. So if I have zinc plus HCl, the zinc can displace the hydrogen in that case to form zinc chloride, and the hydrogen also will evolve. If I looked at the oxidation number in that case, for zinc it was 0 and it became positive 2. As for hydrogen, it is positive 1 in that case, and it is positive 1 in that case. And for chlorine, it didn't yet change. It is minus 1 in that side, and it's minus 1 on that side. Hydrogen can displaced in absence of water. So it can be displaced by something like zinc from their acids. So if I reacted zinc with hydrogen chloride, it will form zinc chloride, and so the zinc will replace the hydrogen, and the hydrogen gas will evolve in that case. And if we looked at the oxidation number of zinc, here was 0, and on that side it is positive 2. If I looked at the electronegativity series, the electronegativity series, it defines which part will replace the hydrogen or be replaced by another element. If I wanted like to know if this metal or this element will replace the hydrogen or not, I have to look at the electronegativity series. The electronegativity in general, it's the property that describes the tendency of atom to attract or share a pair of electrons toward itself. The higher the associated the electronegativity, the higher or the more tendency to attract the electron towards it. Example for that, in that case, if I looked at those elements will replace the hydrogen in their in their molecules, while those parts actually cannot replace the hydrogen. So I have here weak oxidizing agent, while here it's a strong oxidizing agent. I name those parts the stronger oxidizing agent because they can take out the electrons from this another half. If I looked at the metal displacement, less electronegative can replace the active metals. So in that case, if I looked here at the electronegativity series, now it's not so it's not just the hydrogen that can be displaced, because I have in electronegativity series I have atoms that elements that below the hydrogen. So all metals that can be displaced or less electronegative active can be displaced or replaced by more active or more electronegative metals. So this metal displacement usually we can use it to pure metals from their ores. So if I try to look at vanadium oxide with the calcium, the vanadium in that case will be replaced with calcium in their oxide to form calcium oxide. So I have here the vanadium element is replaced by the calcium to form calcium oxide, and the vanadium will be in that case, if I'm trying to purify vanadium, I can get pure vanadium metal, pure vanadium element from vanadium oxide. Another example the purification of titanium from titanium chloride. If I reacted titanium with magnesium, because magnesium is higher in the electronegativity series, while titanium is actually in the lower part of the electronegativity series. In that case, the magnesium will replace the titanium, and I will be able to get a purified titanium metal, and magnesium chloride will form. Now halogens displacement can happen as well. In that case, the more active halogens can replace the less active halogens. So something like fluorine or chlorine can replace the iodine or the bromine. Example, if I have Cl2 that reacts with KPr to give me so the chlorine atom will replace the bromine atom to form KCl plus Br2. Another example, also the replacement of chlorine atom for iodide atom in sodium iodide, and in that case sodium chloride will form and iodine will be produced as well. In general, all halogen are strong oxidizing agents, but the more active ones can replace also the less reactive ones. Now let's look at last type of oxidation reduction reaction, disproportion reaction. In this type of reactions, the element will be oxidized or reduced simultaneously. We mean by simultaneously that one element will happen to this element an oxidation and reduction in the same reaction. Example for that, if I have chlorine gas that reacts with hydroxide in aqueous solution, I will have ClO minus, which means in that case chlorine would be equal to positive 1, and in here it was equal to 0, and in that part the Cl chlorine ions will be produced as well with negative 1, and also water will form. If I looked here at the chlorine, it was in that case in chlorine molecule it was equal to 0, and in the formation of ClO minus it was equal to plus 1, and the formation of chlorine atoms in ions in water it was equal to minus 1. Now let's try to look at those following reactions to know to classify them which type of oxidation reduction reactions. So the first reaction 2N2O to give me 2 nitrogen gas and oxygen. I have here one compound that decomposes into 2 compounds. This is why I consider this reaction to be decomposition reaction. And the oxidation number, if I look at the oxidation number for oxygen, that side is equal to 0 and on that side is equal to minus 2. This is why I consider this reaction to be oxidation reduction reaction, and because I have one compound forms 2 compounds, it is a decomposition reaction. The second example, 6 lithium reacts with nitrogen gas to form lithium nitride. In that case, I have here 2 components that combine together to form one compound. This is why I consider this reaction to be combination reaction. And the oxidation number in that case for lithium here was 0, for nitrogen here was 0, and in that side is actually minus 3. This is why I consider this one to be oxidation reduction reaction. Nickel reacts with lead nitrate to form lead and nickel nitrate. You could see that the nickel actually replaced the lead in its compound, so this is why I consider this one to be replacement reaction or displacement reaction. And the displacement reaction here it's oxidation reduction of course, because I have here nickel is 0 and lead is 0, and the oxidation number of nickel and lead on that side is actually positive 2. If I looked at the last example, 2NO2 plus water to give me HNO2 and HNO3. If I try to calculate the oxidation number of nitrogen in that case, in that compound in O2, it's equal to 0. This means nitrogen would be equal to positive 4, because oxygen is equal to minus 2 and I have 2 atoms. If I calculated for HNO2, this means the N should be equal to, if I have here the hydrogen is equal to positive 1 and each oxygen is equal to minus 2, this means I have here nitrogen is equal to positive 3. For this compound HNO3, nitric acid is equal to 0. This means I have here positive 1, but for oxygen is actually each one of them is equal to negative 2. This means I have here negative 6. This is why nitrogen would be equal to positive 5. So I could see here that there is a different oxidation number for nitrogen in the same reaction. This is why I consider this reaction to be disproportion reaction. By that we came to the end of this video and the end of this chapter, chapter 4, reactions in aqueous solution. Thank you and goodbye.